Please share the screens.
Oh, yes, thanks. Okay. All right. So good afternoon, evening, everyone. So we are recording now. So let's start with the example we saw last time at the end, right? So I gave it as a try it yourself problem to choose a maximal matching and then run the algorithm and see whether you find a perfect matching or you don't find a perfect matching, right? So did anybody try this? No? Okay. So if you haven't, let's do it now. Can you give me a maximal matching in this? Sorry, W3U4. Okay, let me W3U4, W1U1, and W2U2, U2U3, whatever. Okay, let's do this. Okay, so that clearly is a maximal matching. So we could have started with that matching and then run the algorithm. Right? So let's do that. Yes, right. You mean this one, right? Okay, so let's start with an exposed vertex, which is in the color class, the black vertices, right? So let's start with the vertex U3. And let's look at all the neighbors. So we get W1 and W2. And this time I'm going to do it a bit faster. Notice that we don't need to look at each level separately. So when I see W1, I see that it is already a matched vertex. So I can immediately add the next edge, W1, U1, right? This is a matching edge. And similarly, when I see W2, I can add W2, U2 together. And these are matching edges. So let me just color them red. Okay. And now let's see what we have at U1 and U2. So U1's neighbors are exactly W1 and W2, which are both already in our tree. And U2's neighbors are also simply W1 and W2, which are also in our tree, right? So at this point, we can't really build this tree any further, right? All the vertices we see at U1 and U2 are already in this tree, right? So at this point, we should be able to, so in this case, we are not going to find an augmenting path. Does everybody agree? And when we can't find an augmenting path, we want to find a deficient set. And in fact, that will be the case as per this algorithm. So can anybody see the deficient set here? U1, U2, U3. So look at the current black vertices in your tree. And if you can't find an augmenting path, those black vertices will comprise a deficient set. So in fact, we look at these three vertices and their neighborhood is exactly two vertices. Right? So the graph in fact cannot have a perfect matching. Yeah. Okay, it's a small example, but hopefully it still conveys the point. Right? You could have built this tree for quite some time and eventually reached a situation where you can't build it any further. At that point, all your black vertices, because we start with a black root, they will comprise a deficient set. And notice that the neighborhood will be exactly the white vertices in your tree, which is always one less than the number of black vertices. So now that we have done one example of each, are there any questions or concerns at this point? No? All good? Okay, so we have done one example of each, right? In one example, we got a perfect matching. In the other, we get a deficient set. So let's write down an algorithm. Let's formalize everything. and let's write down an algorithm. So formalizing. So notice that at any step in your algorithm, you will have this tree, right? And what does this tree look like? I won't use different colors. I'll make it a bit faster. So this tree will look like this. You could have more neighbors here. Right? So this is your tree at any step of the algorithm. And this is the root of your tree, the exposed vertex where you started. Right? So what are we doing at any step of the algorithm? So I want to first focus on the general step, and then we'll think about termination, initialization, all those things. Okay? So at any step in the algorithm, what is it that we are trying to do? Okay. No, so let's say we are at some step of the algorithm, right? So at this step, what is it that you're going to look at? What are the edges of the graph that you want to look at? So we are at some step of the algorithm. We've got a tree, we have a root, and this is what the tree looks like. So what is it that you are examining at each step of the algorithm? Okay, so you are looking at the leaves of this tree. That's a good start. And you are looking at vertices reachable in the tree or in the graph. Okay, sure. So we have already started at the root. When we started the algorithm, we started at root. Now we are at some tree. The root is never going to change. Well, the root right now is what it is. Right, leaves. Right. So, okay, so we can either look at the leaves, but I can just do something slightly more general, right? I can look at all the black vertices, and I can look at any edge which starts at a black vertex in the tree and whose end is not in the tree. Okay. So when you implement it, you can prune it further. But right now I want to look at it at a slightly higher level, right? So I'm going to look at all the black vertices of my tree and look at those edges which are going from a black vertex of the tree to the outside of the tree. Okay, so if that edge is here, then that is exactly like a leaf you are saying, right? But I'm not going to focus too much on the leaves right now. You can do that when you actually implement to make it even faster. Right? But the main point is that if you find any edge going from a black vertex of the tree to outside the tree, then this is an M-augmenting path if this vertex is exposed. Right? And if this vertex is not exposed, then I'm going to include that vertex and its neighbor inside my tree. Right? Okay. So let's say for each, let me say if there exists an edge UW such that U is in my tree and it is a black colored vertex and W is not in the tree. Supposing there is such an edge, right? So I can just scan all the black vertices and look at their neighbors in the tree. If there is such an edge, then so this is, think of this as your U and this as your W. I'm deliberately not picking a leaf because I don't want to get into those very specific details that will make the algorithm very long. I'm just looking at any vertex. All right. So if I get such a edge, then what should I be looking at? Now, what is the next condition I want to look at? Sorry. Right. Let's check if W is exposed or it is not exposed. Right. So if W is not exposed, if W is okay, let me just do first exposed. That is easier. If it is exposed with respect to the current matching, right? So the current matching edges are all the edges that look like this. Some of them are in the tree and some of them could be outside. If this vertex is exposed, then what should we do? Right, then we get an M-augmenting path and we update our matching and we repeat whatever we are doing. Okay, so then let Q denote the unique RU path in the tree. Does everybody agree? Between any two vertices, there is a unique path plus the edge UW, right? And when I say path, I'm thinking of a path as simply a set of edges, right? Not considering the vertices. Okay. And what should I do now? So I got this path. This is an augmenting path. And how should I update my matching? Symmetric difference with this path. So let the matching be the current matching symmetric difference, this path. Okay. All right. What else should we do now? We have changed the matching. What else do we need to change at this point? The tree. We should restart. We should reinitialize the tree completely, right? So how should we initialize the tree now? So I'm going to throw away this tree and I'm going to start with a new tree altogether. Remember last time that's what we did. Every time we got a bigger matching, we started constructing our tree again. Okay, start afresh with another root, which is a name exposed vertex in the black color, right? There is one problem though. Something could have happened. Something good could have happened. Perfect matching. So if it is a perfect matching, okay, so let me be consistent in my notation. If M is a perfect matching, then I want to return this matching, right? Okay. If it is not a perfect matching, then there is some M exposed vertex which is black colored because the number of black vertices is equal to the number of white vertices, right? So in that case, else, so this else is matched with this corresponding if with 3 lines. Else, I'm going to reset my tree to be any vertex R and the empty set as the set of edges, where R is any M exposed vertex in black color. Okay. So this finishes our second if statement. Now let's see what happens if that condition doesn't hold. Okay. So if the vertex I'm looking at is not an exposed vertex, then it means that it has been matched to some vertex. And what should I do at this point? Add the two edges in the tree, right? I'm going to add both edges UW and the unique edge at W, which is in the matching. Both of them I'm going to put it in my tree. Okay. Else, add UW plus, look at the edges incident at W and look at the unique edge which is in this matching. And add both of these edges. So notice that this is simply two edges. And when I add two edges, I of course add the corresponding vertices. Add two edges to the tree T. Okay. All right. And is there anything else we should do at this point? Right, we have updated the tree, so we should be good to go, right? There's no other changes to be made. All right, let's come to our first if statement. So what was the first if statement? There is an edge which starts at a black vertex in the tree and whose other end is not in the tree. So what if there is no such edge? Right, then we should have a deficient set, right? Okay, so in this case, we want to return the deficient set. And what is the deficient set going to be? All the black vertices of the tree, right? Exactly. So else we are going to return the deficient set D, which is the tree intersect all the black vertices. Oh, they are not black, B, it's U. So, okay, so let me just. Okay, so it's all the black vertices of the tree. Okay, good. So this is how the algorithm looks at any step. We need to do the boring stuff, right? The initialization. So let's do that. So how should we fill up these lines? What are the things we need to initialize before we get to the actual loop? Also, this is a loop that goes on forever, right? At some point you will return, that is when the loop will end. Okay, so maybe it's say okay, so what should I initialize? M and T, right? So that so you could start with the empty matching. I just think it's a bit silly. I like to start with the maximal matching, right? So we can start with any maximal matching. Then you can find this by greedy algorithm. And what should our tree be? Okay, we should also check if the maximal matching is perfect. So let's do that. If the maximal matching we found happens to be perfect matching, then return this perfect matching. Otherwise, you start your tree and it's the same thing that we wrote earlier. It's a arbitrary root with no edges and R is any M exposed vertex which is black in color. Right? So the only point I want to make here is M equal to MT is also valid. In which case you will just keep finding edges in the loop and adding them to your matching. Okay, good. So notice that this is pretty bare bones structure of the algorithm, right? Last time when we were discussing, we were doing all this level business. That is useful when you're actually implementing it. Because if you did not find any outgoing edges at this vertex in a previous step, then you also will not find in a later step. So you could keep track of the last level and you could just scan the last level vertices, which would be the leaves of the tree, right? But anyways, that's just a minor pruning. It will improve the polynomial time slightly or maybe even not that. So just a remark. in an implementation, one may keep track of the level to make it more efficient. Okay, but I hope everybody kind of sees without doing the full analysis that this is already a polynomial time algorithm, right? And the correctness of this algorithm, which you may or may not prove on an assignment, I'm not sure, implies Hall's theorem, right? This is also a proof for Hall's theorem because this algorithm will always terminate with exactly one of two possibilities, either a perfect matching or a deficient set. So you get Hall's theorem for free from the correctness of this algorithm. Okay. Are there any questions or concerns? Anyone in the call? All right. So if not, because in that case, I want to start a new page. Okay. Okay, so now I want to switch focus to finding a minimum cost perfect matching in bipartite graphs. So next goal. Right? Eventually, we want to get to finding a minimum cost perfect matching in all graphs.
The new page is not visible to us.
Oh, thanks. I think I need to, yeah, you're right. Okay. Okay. Is it visible
Yes,
now?
yes.
Okay. Thanks, Shantini. Okay. All right. So eventually we want to get to finding a minimum cost perfect matching in all graphs, but that requires significantly more sophisticated ideas, right? So we'll get there eventually. Before that, we'll also have to see how to find a perfect matching in general graphs. So that will be the next step. Okay. So let's focus on this for now. Okay. However, today's discussion will largely be applicable to all graphs. Okay, we won't see the whole algorithm today. The algorithm we'll be seeing is only applicable to bipartite graphs. But today I just want to look at the ILP, the LP relaxation, the dual, the same kind of thing but that we did in shortest path. Right? So it's the same recipe. Right? So all right, so let's consider the ILP for the minimum cost perfect matching problem. Okay? So what do we have? We are given a graph G and we are given costs on the edges. Okay, unlike the shortest path problem, here the costs can also be negative. So we are trying to minimize, we are trying to pick a set of edges that will be a perfect matching, and we want to minimize the cost of the perfect matching. So we are trying to minimize the cost subject to what are the constraints? What do we want this to be? 1, right? At each vertex, we want exactly one edge. We want our variables to be non-negative. And of course, in the ILP, we want them to be integral. All right. So let's call this P prime, and let's write down the relaxation, which is the same thing without the integrality constraints. And let's write down the dual of this LP. So we are maximizing 1 transpose Y subject to A transpose Y, something C. And what are the Y's? Y's are free. Okay, that's easy. And what about this sign here? Less than equal to, right? Okay. So let us try to understand what the dual is trying to do, right? So an interpretation of the dual. Okay, so what is a dual? How can I look at a dual feasible solution? These are the labels. Okay, so for each vertex we have a label which is the corresponding dual variable. They are real numbers, right? And what are the constraints we want to satisfy? Okay, some of the less than equal to cost of the edge. Okay, good. All right. So each vertex V is associated with a dual variable, also known as the labels, right? YV. Dual, let me call it a real variable. It's not non-negative or non-positive. It's just any real number. And such that for every edge UW of the graph, we have that YU plus YW is less than equal to the cost of the edge. Which in other words, you can think of it as this. You can think of it as the cost of the edge minus the labels of the two ends is greater than equal to 0. So that is what a dual feasible solution looks like. All right, and let's do the standard stuff. Let's try to think about weak duality and complementary slackness, and let's try to get combinatorial interpretations of those. Okay, so let's consider weak duality. So let's say I have a feasible solution to the primal and a feasible solution to the dual. So what is less than equal to what? Sum of the labels is less than equal to the cost of the, yeah, right. So the dual is a maximization problem. So one transpose y bar is less than equal to C transpose X bar, which is the same as saying that sum of all the labels is less than equal to C transpose X bar. And in particular, so as we did in shortest paths, we are always going to have a dual feasible solution in our algorithm, right? And with respect to this, we will try to find some perfect matching, right? Which will correspond to a primal feasible solution. In particular, at the end, we want both a dual feasible solution and a perfect matching. So in particular, if M is a perfect matching of the graph G, and if Y bar is feasible, let me just abbreviate it to DFS. If Y bar is my dual feasible solution, then what weak duality is saying is that the sum of the labels is always going to be a lower bound on the cost of the matching, of the perfect matching. Right, so this is what we call it as a sort of combinatorial interpretation of equality. And now let's think about complementary slackness. Okay, so let's say we have a feasible solution to the primal, and we have a feasible solution to the dual. So the complementary slackness theorem says that both of these are optimal, optimal for P, and y bar is optimal for the dual if and only if the CS conditions hold. There is only one CS condition. Okay, and what is that? Right. So there is a, for each UW edge of the graph, I'm going to reverse the order. So either the y bar u plus y bar w is equal to the cost of the edge, or the x bar uw is 0. And that is the same. Okay, so that's for primal and dual feasible solution. And now let's try to think about this from a matching point of view, right? So if M is my perfect matching of the graph G, and y bar is a dual feasible solution, so if for every edge, if for each edge of the graph, if this is not true, right? So which means that if the edge is in the perfect matching, right? If the edge is in the perfect matching, then I need the corresponding dual variables to add up to exactly the cost of the edge, right? If E belongs to the perfect matching, then it must be the case that the two dual variables add up exactly to the cost of the edge. If this is true for every single edge of the graph, then it means that you've got a minimum cost perfect matching. Then we have got a minimum cost perfect matching and an optimal dual solution as well. Then M is a min cost perfect matching, and y bar is an optimal dual feasible solution, and therefore your certificate of optimality. So everything we have discussed so far, notice that I have not written both directions of complementary slackness. I've written only one direction. If we can find a perfect matching and a dual feasible solution that satisfy these conditions, then for sure that is a perfect matching of minimum cost, and the dual solution is an optimal one. I'm not stating the converse. So everything we've discussed so far is applicable to all graphs, not just bipartite graphs. What is interesting, and I want to show you an example later, I don't have one right now off the top of my head, is so we will see an algorithm for min cost perfect matching, which will actually satisfy the conditions at the end, right? I mean, that is what we did in shortest path also. At the end of the algorithm, you found a path and you found a dual feasible solution. They satisfied the CS conditions. Therefore, the path was shortest and the dual feasible solution was optimal. In the same sense, we are going to do the same sort of thing for bipartite matchings. Our algorithm will find an n and a y bar that satisfy the dual feasible, the CF conditions that we have stated here, right? And therefore, we will know that it is a minimum cost perfect match. The problem is that exact algorithm doesn't work for all graphs. Okay, and that is related to a certain phenomenon that in the case of bipartite graphs, it's related to your assignment. Was it 2 FMP PMP? Right. So this phenomenon is related to your assignment 2, where the fractional matching polytope and the perfect matching polytope, they coincide for bipartite graphs. They are exactly the same. But for non-bipartite graphs, they are not the same. The fractional matching polytope is bigger than the perfect matching polytope in general. Right? So that is sort of the root, one of the root reasons as to why the algorithm will be seen doesn't work for all graphs, and we need to do something more sophisticated for general graphs. Okay. Good. That is all I actually have to say for today. I haven't prepared anything further, so I'm going to stop here. We'll continue tomorrow and we'll see the algorithm for min cost perfect matching for bipartite graphs. Okay. Okay, but this is the key driving sort of key, what is the key observation for our algorithm, just like in the shortest path. Okay. All right. So that's all for today. If there are any questions or concerns, please mention them. Okay, all good. Thank you. Anyone in the call? Are there any questions or concerns? All right, so I'll stop recording.